Hi everyone, I'm Professor Afur from Professor of Mathematics at University of Dayton. Today I'm gonna try to apply some of my research, what I do to model the spread of coronavirus. Everybody is worried about how it's spreading, how many people will get infected, how many people will die, how long will it end, and so forth, and what are the parameters uh, that we can control to control the disease. Okay, so let's say we have a world population. Let's say N equal the world population. Now the world population is going to be divided into three categories. Those who are susceptible, S mean people who are susceptible. It's going to be I, people who are going to get infected, and R is going to be people who are removed from the population. So basically R is people who recover plus people who die. So these people are basically removed from the population. So based on this, we're gonna have S plus R plus I equal to the world population. The world population is what, like 7.9 billion now? Okay, that's not important. Okay, so we have three things. Those who are susceptible, those who are gonna get infected, those who are removed, whether to death due to the infection or to being healed or being recovered. Okay, so you see, in calculus, you always study the derivative. What is a derivative? The derivative is basically the rate of change. Everything in life depends on time. So the rate of change here is with respect to time. That means if the derivative is S prime, for example, so basically we're gonna take a look at, I'm gonna erase this, remember S susceptible. So basically we're gonna take a look at S prime of t. Okay, so basically this is nothing but ds over dt. This is the rate of change of those who are susceptible. Okay, rate of change of those who are susceptible and so forth. Okay, so now let's see, we have a model and I have taken a note, so so we're gonna have SIR. I've already done that. So it's going to be S prime, I prime, and R prime. Okay? So this is the rate of change. All right, so let's say, so we have people who are, basically we have susceptible, they go into infected, and they go into removed from the population. So to go from here to here, to go from susceptible to infected, you have to have a contact. So to go from here to here, you have to have a contact. The contact is SI between the two. And there is some parameter of infection which we're gonna go call beta. I want to make sure. Yes. So beta is the rate of infection. It's like the infection constant. Now, remember, this is a population, so this will be population squared. We want it to be population, so we're going to divide by the total number of population, which is n. Okay? So now, I will tell you what beta is. And from here to here, you're going to go, some parameters is going to be gamma I, okay? To go from there to there. So let's see what we have now. So I I prime to go from I to R, so the rate of change they lost minus gamma I. Minus gamma I here, because the rate of change lost gamma I into R. Okay? Now, 2 R prime is gonna, so if I loses gamma I, R will gain gamma I. So it's gonna be gamma I. Okay? All right. A plus beta SIN. Why? Because remember, these are the entered into infected. Beta SIN. They entered into the infected. And then we have S prime. They left those susceptibles, so that is minus beta SI over N. So that is the model. Now, beta and gamma are very, very important. So beta is constant of infection. And gamma is constant of recovered or removed. So these are very, very important later on. Okay, so this is what we have. Now, this model is very, very nonlinear. So we cannot solve. I cannot solve. So this is where research comes in, and we do some analysis to prove that solution remain bounded and constant and so forth. Okay, so based on the last few 10 days, this is time, and this is number of infected. The graph was growing exponentially. So that is very, very scary. In a very short time, the whole population of the world will be infected. But we know people, government are doing things, so like controlling borders, closing airport, people are staying at home, and people washing their hands, and this one can only be controlled by vaccine. Well, we don't know yet. So this beta can be controlled, this gamma cannot be controlled unless we have a vaccine. So we are hoping that the graph would be something like this. You see? So regardless of how long, 20 years, 50 years from now, the number of infected people will not go above this line. So the question is, what is this line here? What is it? And how do we determine it? So you see what we are doing here? This is what we are looking at. Hi, Lily. So this is what we're gonna do. So I'm gonna do some analysis here and show you how things are done. All right, so I'm gonna erase this. So scientists hope to have this graph instead of this graph. Based on this graph, the whole population will be infected. Here, there will be saturation of this line. That's it. And this is what we are looking after. All right. So let's say at some time, this is initial, T0, we know the number of infected is 1. Why 1? This one is basically scaled down. So it's like, it's very compounded number. It could be million, it could be thousand, it could be whatever. It doesn't really matter at this point. For mathematician, it doesn't matter. So let's say I naught is 1. Okay? So if I do that, I did scratch myself some notes here, then you know S at T naught, I'm still talking about some initial time. Let's say we could say March 1st, when people really recognize the disease. So S is still about n minus 1. This is the total population minus 1. And let's say that is n, because the total population of the world is way much bigger than the initial number of people who are infected. So let's say this is n. So now let us take a look at the rate of change of the people infected at time t naught. So this is gonna be from here. It's gonna be beta. Remember, S is N. I is 1 over N minus gamma times 1. So that is beta minus gamma. So the number beta minus gamma is very important. But you know, I looked at this number for a long time. I couldn't get anything out of it. So I'm going to write this number as beta minus gamma times gamma over gamma. It's like multiplying by 1. And let me rewrite it. So this is going to be gamma beta over gamma minus 1. That is a very, very, very important number. Okay, so let's say what we have now. I really don't need any of this. I don't need any of this. So let me rewrite here. So I have the rate of change of the initial people who are going to get infected is gamma beta over gamma minus 1. So if beta over gamma minus 1 is positive, that implies there are new infected people who will infect others. And in this case, the people, in this case, the number of infection, in this case, I will grows like this exponentially. So, we decided that. So, if beta over gamma minus 1 positive, that implies beta over gamma is bigger than 1, then corona becomes epidemic. It's epidemic. So people hope, so corona becomes epidemic. That means it's something to worry about and we need to control. Now, however, if beta over gamma minus 1 is less than 0, that means beta over gamma is less than 1, then it's not epidemic, no worry about it, people go on with their regular lives, okay? So that number beta over gamma. Okay, so how can we control beta and gamma? All right, so I'm about to get finished. Lily, gonna get out. Okay, we're almost done. All right. So, how to change beta and gamma? Okay. So remember, so we're gonna have beta and we're gonna have gamma. Okay, so beta has to be less than gamma. So remember here, beta over gamma bigger than 1 is a big problem. So we want beta over gamma less than 1, that means we want beta to be less than gamma. Okay, so what does beta, how can we control beta? Okay, so beta can be controlled by 1, closing borders, 2, staying home. Okay? So closing borders, staying home, washing hands. Okay? So this is what we can do. And gamma can only be controlled by vaccine. Okay? So gamma can only be controlled by vaccine. So beta, we have total control over beta. Closing borders, including airports. Are you listening? Including airports. Staying home, washing hands. Okay? Now let me give you some numbers. Okay, I'm gonna give you some numbers. Okay, I went to World Health Organization and I got some numbers. So, okay, so where are the numbers? Okay, so beta, if beta is 0.0724 and gamma is 0.063, you know beta is bigger than gamma here. So beta is bigger than gamma. So beta is bigger than gamma, so we have epidemic. So the limit as t goes to infinity of I plus R is gonna be about 1.87 billion. That means a quarter of the population will get infected and removed. Or removed, between infected and removed. Okay? And that will take, so basically this will take 4 to 5 years to control the coronavirus. So if this is the case, okay, will take 4 to 5 years to control it. All right, another number, if beta is 0.116 and gamma is 0.0405, that limit will be 6.6 billion, almost the whole population. And that will take only 10 months. Okay? Okay, and then I have, and then basically, this is the, I think I can give you more numbers, but it doesn't really, it's not important. So the model tells me to control the disease, the people have to be very careful, they have to stay at home, wash their hands, control, close airport, close borders for a while until the things is controlled. And that is the application of what I do in mathematics. Thank you very much. How's that, Andros?
Oh wait,
What do you think?
you did not stop it, did you?
Oops.